This is All Things ANSYS, a podcast from the technical support staff at PADT. Episode 58, a discussion on a real-world application of topological optimization with user Matt Humrick from Advatech Pacific and PADT's very own Pam Waterman, along with news and events from the ANSYS world. Greetings, everybody, on a nice Monday morning here in Phoenix, Arizona. My name is Eric Miller, and I'm one of the owners here at PADT and your host for these podcasts. Like many companies, we're figuring out the way through this coronavirus COVID-19 thing, just trying to figure out, do we call it coronavirus? Do we call it COVID-19? Do we call it COVID-19, the disease caused by the coronavirus? We're really trying to figure out a lot of stuff. But seriously, I spent most of Friday working on our reaction plan, what we're going to do if we do get the CDC or the Arizona Department of Health says we should work from home, how we're going to do that, make sure everything's in place so we don't miss a beat. I totally forgot to record this part of the podcast. So I apologize for that. So it's going out a little bit late this week. Our advice to all of you on this whole thing is to make sure you can work from home. Fortunately, if you're using ANSYS as your primary tool, that's not a hard thing to do. If you have the hardware at home you can run on, just make sure you can see your licenses at work. If not, make sure that you can, if you can't work from home, you got to use a computer at work, then make sure your VPN is working and that your remote desktop is also working. Or if you're running on Linux, that you can display your Linux windows back or using some sort of a tool that lets you see your desktop remotely, however that's going to work through a VPN. So it's secure. And if you work on secure projects, like some of our employees are doing, they can't view them from home or work on them from home. So you got to go in and, wash, stay in your cubicles, keep that 6-foot separation from folks, and don't forget to clean off your equipment on a regular basis. Don't touch your face too. That's been a hard one for me. So we do hope that this whole thing does not impact your business, and especially that you and yours stay safe. I think it's one of those things where if we use logic and our simulation and engineering analytical skills, we can do well with this, and it shouldn't be too much of an inconvenience as we work our way through it all. And also let us know if PADT can help. If you need any advice on how to deal with anything, especially working remotely, let us know. And whatever else we can do as a company, outside of just the ANSYS side of things, how we can help you get through this. And let's take a look at the podcast itself. As an update, we've had 18,135 downloads over 57 episodes. So that's 318 per episode, which is another advance. So we're working our way back up again. So thank you all of our listeners, and especially those of you who are spreading the word and letting other people know about the podcast. Please keep it up. So this week we have a discussion, an interview. We're always happy to have our customers basically come on and share their real-world applications of ANSYS. And we're especially honored this time because it's not just a customer, it's a partner of ours, Advatech Pacific. And I'll explain why I say they're a partner of ours in the interview itself. And they're going to talk about a project they did where they compared ANSYS topological optimization with another tool and how their part ended up. We're joined on this podcast for the first time, which is fantastic, by Pam Waterman, who is our application engineer, and she has a fantastic background. She explains that when she introduces herself, but she's an application engineer for our 3D printing group. So please do enjoy this discussion about how they use topological optimization to actually design a real part. Thank you. So welcome to today's talk about what actually I think is our most popular topic on this podcast, topological optimization. We've covered it twice, and it's one of the most downloaded. Those two are some of the most downloaded episodes. So I'm really happy to have a real-world application of it. And with me today, I've got Matt Humrick, Advatech Pacific, who is an engineering manager there, and our very own Pam Waterman, who is an application engineer for 3D printing here at PADT. So, Matt, why don't you introduce yourself, what you do, what does Advatech do, what do you do? And I always like to find out, how'd you end up being doing simulation?
Thanks, Eric. Yes, I'm Matt Humrick. I work for Advatech Pacific. I'm an engineering manager there. And we're an outsourcing company. So we help other companies find solutions to their problems, primarily in aerospace. We have a lot of experience in aircraft, helicopters, rockets, satellites, space vehicles, marine applications, power generation, gas turbine engines, quite a wide range of things. And I've been doing analysis for, well, close to 20 years on and off. Mm-hmm. When I graduated school, I actually went into design and did a lot of 3D modeling with CAD. But I always loved the more analytical part of engineering. I love numbers, and so I always felt drawn to doing analysis. It took me a few years, but eventually I got the opportunity to start working with some other engineers, mentored me, and got me into structural analysis, and been doing it ever since.
Very cool. Yeah, and PADT and Advatech work together quite often. Both you guys help us with design and some simulation outsourcing, and we've done some simulation outsourcing for you guys. And the original founders actually used to work with us back in the day at Honeywell. So what's now Honeywell. So we're not just a customer, but a partner of PADT. So we love doing work with you guys. Pam, your story. Have you ever been on the podcast before? I don't think so.
No, this is the first pleasure.
So why don't you give us the long version of your journey to being an application engineer at PADT? It's a very interesting story.
Yeah, wanders a little bit from the traditional.
Yes.
My degrees actually are much more in microwave engineering and radio astronomy, with a specialty in antenna and amplifier design. But I started out as a manufacturing engineer at Raytheon back on the East Coast. Got thrown into the hardware, really loved it. Had also done paper and pencil finite element analysis in grad school. So
nice.
That gave me a little background, for doing things like ANSYS and simulation. Worked for MITRE, did satellite communication design for quite a bit, and then kind of sideways into technical writing, which gave me my first introduction to 3D printing and additive manufacturing. Been in that field one way or the other for more than 20 years. Have loved seeing the evolution of additive and seeing how it's all coming together and the software is merging and catching up with it, allowing us to make parts that we previously could design but never make. I even had that in grad school. The part that I designed for an antenna could not be machined. So it'd be kind of cool to see that made someday. So now I've been at PADT almost a year and a half, have known you all for almost 20 years, and really, really am enjoying getting to help customers and prospective customers see the benefits and possibilities of additive.
Mm-hmm. And as the listeners of this podcast know, I love when we can combine the things that PADT does, design, 3D printing, and simulation together, which is what we're talking about today. Using design to drive using simulation to drive the design of a part that is made with additive manufacturing. So before we get started on the talk, I will point out the fact that this is going to be a really difficult discussion because the parts are really cool and we're talking without pictures. So we will link to some content that will describe in more detail what we have and some images and things like that Pam has put together for some marketing material, and we'll definitely point to that stuff. So it'll help the listeners can go find that in the links underneath and take a look at what we're talking about. So, Matt, why don't you explain to us what this project was about?
This project grew out of our support of our customer. They have a legacy gas turbine engine family that they are, again, supporting and also adapting to new market opportunities in power generation. And as part of that effort, we help them with several things like part obsolescence, reducing cost, either through redesign or using new technologies like additive, or even redesigning parts or entire engine modules to meet new exhaust emissions requirements. So we've already helped them transition several of their parts to additive, things like combustor nozzles, things like that, smaller parts that generally require complex castings. But we also wanted to show them the benefit of combining additive with the topology optimization.
Cool.
So for this project, we selected something that was simple. So this is is just basically a beam with an eccentric load applied to it. The part itself is a torque arm that connects a linear actuator to a bell crank assembly that activates the inlet guide vanes for the compressor module.
Okay.
So we selected that part, again, because it was something simple and something that still had sort of an intuitive solution. So you could compare what you got from the topology optimization to kind of what you would expect from a classical hand calculation.
Mm-hmm.
And you could also see where it might deviate a little bit. So as we also at the same time, we were trying out both ANSYS and another software package to see how they perform the topology optimization.
Good.
So it was kind of a combination of comparing these two different software packages, as well as demonstrating the benefits of topology optimization to our customer. So the first step was to create the CAD model from the drawings. CAD models didn't exist for these parts, and then bring the whole bell crank assembly into ANSYS Mechanical and just do a baseline structural analysis to start from.
Okay.
So the next step was to do the topology optimization, and for this, we wanted to minimize weight, but there was an additional requirement that this would be considered a drop-in replacement. So we wanted to match the stiffness of the original part, the bending stiffness, so that we didn't alter the behavior of how the bell crank assembly worked.
Good idea. Yeah.
So I guess the competing solution, that product was designed more for designers,
mm-hmm.
and it took a very different approach to how ANSYS does. And their user interface was a lot more graphical.
Okay.
It's not very data driven. It's very much more visual.
Mm-hmm.
It was simple enough to use, but
right.
Probably more challenging for me as an analyst versus
mm-hmm.
a designer.
Yeah, right.
Then I'd say the main limitation with that package was that you could only include one part. You couldn't have a whole assembly in the analysis. So I could only have the torque arm in the model, and that forced me to use basically just a rigid constraint where the torque arm fit onto the bell crank shaft.
Okay. And that wouldn't be very realistic.
No. So it ultimately gave basically something that was more in line with what you would get from a hand calc. So you had a perfectly symmetric shape.
Mm-hmm.
It wasn't, I would say the final shape wasn't as usable as what I ended up getting out of ANSYS.
Mm-hmm. Mm-hmm.
So using the ANSYS Mechanical, I was able to include the entire bell crank assembly in that model, which allowed me to include the actual frictionless contact between the torque arm and the shaft.
Very important, yeah.
Yeah, and that actually proved to be critical, because when you apply the load to the torque arm, the elasticity of the torque arm and the shaft causes the inside edge of the torque arm to load up and versus the outside edge. So there's an asymmetry in the actual load and how the load is transferred from the arm into the shaft.
Mm-hmm.
So that was a real driver for the optimized solution. So, from classical beam theory, you'd expect the torque arm to look sort of like an I-beam.
Right.
And ultimately that's the general shape that we got, but instead of a vertical web down the center of the beam, it actually created a sort of a wavy web where it started out in the middle and then curved towards the inside edge that was loaded.
Gotcha.
So that was something that, you wouldn't have kind of predicted just based on hand calcs.
Cool.
Yeah. So definite asymmetry when you look at this part.
Look at the part.
In multiple directions.
Well, it brings up an important thing that, both Pam and I, we have a workshop, and Pam mostly teaches it, that on design for additive manufacturing, and kind of hints for design engineers to make better parts for additive. And when we talk about topological optimization, one of the things we really stress is you got to model the loads correctly, because the shape is driven by those loads, that load path, right? So this is a great example of that. When you simplify the loads, you don't get that asymmetry that you need, that you can benefit from. So it's a good example. Yeah.
Mm-hmm. And then you talked about how you brought that into the CAD package. Can you talk us through that a little bit?
Yeah. So ultimately, there's some other features in the ANSYS model that didn't show up in the competing package as well. For example, in order to reduce weight, you can create, sort of a lattice structure with your web.
Gotcha.
So with ANSYS, it was sort of crude, but those features were present. You could tell that that's kind of the direction it was heading. Whereas with the competing package, it basically just created a solid web with a couple of small holes in it.
Gotcha.
So I would say the finished optimized part from ANSYS was definitely closer to what you would end up using. So once we had that, obviously you get a very organic shape that isn't necessarily what you actually want to manufacture. So the next step was to get that into CAD and sort of clean that up into something that you could produce. And really that was the part that took the most amount of time. So for this, I brought it into CAD, and I basically just took a bunch of cross-section cuts through it, so that I could capture the beam flanges, which were also tapered, again, which you would expect for a beam and bending. So those were tapered, and then obviously the asymmetry in the web. So yeah, I just took a bunch of cross-section cuts and then used those as guidelines to construct a new CAD model based on that geometry. So that's a really good point. Now I kind of want to pause at, because this is something we talk about a lot, and I think Pam, you've seen it as well, is the desire to go straight from that mesh that topological optimizer produces and just print that. And I'm an advocate of doing exactly what you did, which is use it as a guide to create a part in a more traditional way. Do you feel that was that you needed to do that? I mean, what are the reasons why you didn't just go straight from the FEA model and say print this? Well, with the optimized part, you have sort of an organic, sort of rough shape, and it's in a way it's sort of unfinished. And it's also dependent, of course, on your mesh density. If you have
very good point. Yeah.
A super refined mesh, you might get a finished shape that is actually pretty close to what you would want to print. But maybe you have again, because I was using a whole assembly and stuff, it was as your model size goes up, obviously the runtime goes up as well. Yeah. So you kind of have to keep, it's a trade-off. You have to keep your mesh density within reason. So if you have a whole assembly, or if you have a very large part that forces you to use a bit of a coarser mesh, your finished optimized solution, again, is going to be a bit more jagged, and you're going to have holes and missing pieces. And, you can actually have, because it's basically just deleting elements as it goes through, especially if you're using a TET mesh, you delete a TET, well, now you have sharp corners and sharp points in your finished product, which are just stress risers. So you need to be able to smooth those away.
Good point.
So I'm sure, there's certainly applications where you could go direct to print, but this wasn't one of them.
Yeah, my opinion is those cases are when you're making a model for marketing and not for use in production. But
well, for one thing, because it's part of an assembly, you're going to have finished faces because you're going to be mating to other parts, right?
Yeah, that's true as well.
Yeah, cool. So
can I ask about the iteration? So after you brought it into CAD, I believe you said then you turned around with your new CAD model and put it back into ANSYS to reevaluate, right?
Yes. Yeah, we put it back in and did another structural analysis, and particularly for the the lattice structure in the web. The optimized model from ANSYS sort of hinted at what that should be, but it wasn't quite finished. So I made some kind of assumptions, taking what it had as a suggestion and then, kind of adding some of my own to that to get the final sort of truss structure there. So when I brought it back into ANSYS and did a structural analysis, I could see in that truss structure that I added that it wasn't quite optimized. There were certain hot spots of stress, some other areas that were not fully utilized. So I tweaked the truss structure a bit to get a more even load share through the web.
Good.
Makes sense. Okay, so you were able to refine it and then go back and change the CAD again a little bit?
Yeah, so I took those results, tweaked the CAD, and then brought it back in, reanalyzed it, and verified that it had a much more even load distribution and that we were obviously meeting our stress targets.
Cool. Kind of a traditional shape optimization step in there before the final geometry. Yeah.
Right.
Cool. And you printed it, right, Pam?
Matt did. He printed it just in ABS and also printed the original CAD, original ARM to compare. So we have a nice visual model just in plastic, but the thought down the road would be that he would print it with some kind of direct metal system.
Great.
Right. So we were able to save, it was the final part was 45% lighter than the original.
Wow. Okay.
And we were able to match the bending stiffness of the original exactly within 1%.
So that's significant. I mean, that's real weight. Yeah. Wow.
Yeah, and that was just a very simple part too. You can imagine a larger part, a more complicated part. You could realize even further gains.
Yeah, I one of the things I like about this example is it's not some crazy funky gee whiz look at that shape when it comes out. You can see that it's been optimized for sure, but it's not one of the electric motorcycles where the frame's been run through topological optimization, looks like a tree or something.
Yeah.
Yeah. I really like it. It kind of shows how, if you could do that to, I don't know, 20% of your components, you could get some real significant weight savings on an assembly. So what was the biggest challenge you faced in this study you did?
Well, I guess for me personally, it was learning the software. Obviously, I was doing the same exact project in two different software packages at the same time. One of which I've never used at all. And I had no training and no documentation for.
Oh my gosh.
Well, congrats.
So yeah, that was a little challenging. With ANSYS Mechanical, obviously I've used it for structural analysis. So at least I was familiar with the interface and sort of the terminology. So I guess that's another point is that, I found the ANSYS solution to be easier for me, again, because I had that familiarity and, its interface with, its hierarchical lists and text boxes and things makes more sense to my left brain than the other solution that was geared more for someone with a right brainer.
It's a really good distinction. Yeah. Important distinction. Yeah.
Yeah. you have to choose the tool that best fits you and your team.
Mm.
Pam,
and at the same time,
go ahead.
Sorry. At the same time, the fact that I keep coming back to the fact that ANSYS could handle the entire assembly. It just seems so much more accurate without requiring you to make a whole bunch of assumptions.
Yeah, exactly. That was really the key.
Yeah, and hopefully we'll get Matt to come on and talk about Matt Sutton here to come in and talk about a project we're doing for a different customer, where we're looking at modeling different kinds of loads, and same sort of a thing, that being able to do a more accurate simulation and less assumptions, we're able to get a better geometry out of it. And in this case, we're looking at some very unusual constraints and loads for this application. So hopefully we'll be able to share that in a month or two. Pam, you were kind of involved in watching this and helping through the process. Did anything surprise you along the way that you were like, oh, I never thought about that before, or that was a surprise?
Oh, the asymmetry of this blew me away, because the original torque arm has such symmetry in it. I think just in the back of my mind, I was assuming, if there's going to be material removed, I wouldn't be surprised to see some sort of like a web lattice structure.
Right.
But then to be able to look at this and go, I can't believe how asymmetric this is. It just did not. Was not in the back of my mind or the front of my mind that I would see such a dramatic difference. And yet, when you really look at the load distribution and how he was able to accurately model it, you go, wow, well, of course that makes sense.
Yeah, I think that's kind of been a discovery process for me. Is it, when we traditionally design parts, right, we go in with our assumption of this is what a part should look like for this problem, and we may iterate a little bit on, try a few different things and put some loads on and see if it works. But we kind of go in with an assumption of this is what the part needs to look like, and this allows us to maybe go down paths we wouldn't have thought of. It varies the thickness along the length of the web. Is that correct as well?
Yes.
Yeah, that's another thing that surprised me. Yeah.
Again,
cool.
So going in with preconceived notions with additive and the topology optimization, first off, you really have to leave that behind.
Yeah, I think that's one of the real advantages to doing topological optimization, is that it doesn't come with those preconceived ideas,
right.
And you're not constrained by any legacy design guidelines.
Oh, that's a really good point. Yeah, it's a really, really good point.
Oh, right. Because we're all brought up like, okay, think from day one. How are you going to machine this? Or how are you going to cast it? And what are the general restraints to that? Flat surfaces or perfectly round holes.
Uniform thickness.
Yes.
It's on my wall I'm looking at right now in my office. I have the first thing I ever designed was as a summer student at Lockheed Missiles, was a lens assembly beam diverger for a laser communication satellite. And I'm looking at it going, those 3 holes I put in it to lighten it weren't even close. I so want to put that into ANSYS topological optimization. And I bet I could probably take 30% of the weight out and increase the stiffness as well. So, but that was 37 years ago. I don't think it's around anymore. I guess another question for both of you to finish it up. We could talk about this for hours, but we'll wrap it up. Is if someone else is looking at a part and going, I think I'm going to try and do topological optimization on that. Matt, you go first. What kind of advice would you give them before they get started?
I would say, again, don't try to force any of preconceived ideas into it. So generally when you start with a part, you don't feed it what you think the finished shape is. You want to basically give it a block of material and let it figure out what that shape is.
Right.
The other thing to keep in mind is, again, the solution size. You're basically doing a series of static analyses, probably a lot of them. So you need to be able to keep your model size in check to keep your runtimes down. You don't want to have to let this thing run for multiple days just to finally get a solution. And don't be afraid. You can always start off with a coarse mesh, run that, and let that sort of guide you, and then you can trim instead of having a huge block, you can kind of whittle it down to what that first iteration suggested, and then start from there with a more refined mesh and sort of work your way down to a solution that way. Also, if you're finding that your runtimes are too long.
Mm-hmm.
And just, sort of another use case, obviously everybody thinks of topological optimization, trying to optimize weight or things, but you can also use it as a design tool. Maybe you have this part or a bracket or something, and you come up with your design. You kind of looking at it as like, that looks like a traditional bracket, but I wonder if there's something better.
Right.
You can just use the optimization as a design guide. Just let it do its thing and see if it comes up with a novel solution that you wouldn't have thought of.
That's a really good idea. Have you played with Discovery Live yet?
I have not. I've seen the demos. It looks really cool.
The shape optimization is coming along with that a little bit, and so it's super fast. It's not going to get as close to a real solution like you did with this one, but for what you just mentioned, kind of using it as a idea generator for designs, I think it's going to be invaluable. I'm looking forward to that. Pam, what kind of advice would you give?
Well, I think thinking ahead for the whole workflow, it's exciting to see how the simulation is coming together with additive as a possible way to produce the part.
Right.
And there's going to be still more, because I look at this part and I think, okay, it's still being printed with a solid plan in mind for deposition, but what if the hidden parts even have a structure to them? A finer refinement of a lattice structure, for example. We're getting now closer to being able to simulate what the resultant stresses would be if I wanted to reduce weight even on the interior, and then fold that back into your optimization software. So I'm looking forward to those capabilities being more useful.
Yeah, lattice optimization within the blockier parts is an interesting opportunity in there. That's coming along. We're finding ways to do that. So cool. Well, I have enjoyed this. I learned a lot. It makes even though I never get to do real work, it makes my palms itch with the desire to go optimize something. Maybe next time I design an award, I'll run shape optimization on it. We'll see.
Before and after.
That's right. That's right. I really appreciate Matt, you sharing your experience with us and helping us learn as you learn through this process, and Pam for your breadth and depth of experience brought to the table and helping us understand the application of this. I really appreciate it. And hopefully we'll have more discussions like this. I can't wait to see. One of the best parts of these new capabilities is people are using it in new and different ways that we didn't think, and I can't wait to see more. So I really appreciate it, and thank you guys very, very much.
You're welcome.
Yep. Thank you, Eric.
Okay.
Okay, guys, thanks. I'll edit out that little blank period in there, but I think otherwise it went really well. So we will edit it up, and I stick a little intro before it, and then I talk about news and events after. And I don't know if we're going to publish it this coming Monday or 2 Mondays from now. It depends on I've got another interview with Doug this afternoon, and I can't remember. Trevor told me which one was going to go out first. And then Pam, the case study, is it published or is it?
No, okay. Matt, I think it's in your hands at the moment for final review. Yeah,
we're looking at that now, so I'll send that back over today. I took a quick read through it and it looked fine. So
okay. Awesome. I think that's what Trevor's waiting for. So I think I'm going to do Doug. Doug's going to go out Monday, and then we've got 2 weeks to iterate on the case study. So it really would help people to actually see the part.
Yeah,
because it really does look cool. All right. Thanks, guys. I really, really appreciate it. I hope to have you back on soon. Thanks.
Yay.
All right. Thanks. Bye.
Bye-bye. All right. So that was a great discussion, and hopefully you found it as useful as I did. But let's be honest. For a while, topological optimization, it kind of hit the headlines about 5 years ago, and it was a bit of a science project. There was not many real-world applications for it. But over the past couple of releases, it's become a more practical tool. I think that the ANSYS tool especially has become more practical when compared to other tools out there. Like maybe it got something out quicker, but it really wasn't all that useful. useful. Again, it was more of a science project. And as usual, ANSYS took their time and has come up with something that's useful. And we plan on using it more here at PADT with our customers' projects as well. So we hope you got that feeling from that. And it's a great example. Do check out the release notes for this podcast. They'll be at the bottom of the whatever podcast tool you use to listen, and a link to so you can download the case study and see what the parts look like. Also, do check out Advatech Pacific. They're a great company and do really great work, and we use them. I can't give them a higher set of praise than that. Than when we need help, we don't have the capability in-house, and we need some help with simulation, or especially when we need some help with design, we go to Advatech, and they're fantastic people to work with, and we've known them for probably longer than all of us want to admit. So good stuff. And speaking of recommending who you should work with, you should also consider PADT as your ANSYS supplier if you are in the Southwestern U.S. and for simulation consulting and customization. And by the Southwestern U.S., I mean the states of Texas, Colorado, New Mexico, Utah, Arizona, Nevada, and all of California. So do consider us as your partner for ANSYS. We're also just as good at additive manufacturing and product development, so give us a try. We love what we do, and our customers tell us that we're good at it. So please do consider PADT as your partner in a lot of different ways. All right, let's move on to the news. Let's talk about the ANSYS stock. Speaking of the coronavirus, ANSYS stock, I think last time we talked about how it hit an all-time high, everything was looking good, and then boom, it hit the entire market. As of this morning at 9:30 Phoenix time, which is 9:30 Pacific as well, daylight saving time is over, so we're now at their time. It was down to 228.55. So that is not a lot of fun. Not a good drop. Not much that ANSYS can do about it, of course, because it's determined by the overall market. So it's a little bit up right now. It's at 230 right now. So it went back up a little bit. Let's see, it's 10 o'clock now. So, it's going to move up and down. It's going to do all sorts of crazy things. This is where my ignorance of the stock market come in. I don't know what to do. What's the baseline? All that stuff. But year to date, the S&P is down 8.11% since January 1st, and ANSYS is only down 7.47%. So that's really not too significant considering how high it went up. Remember, it almost crossed 300 there. So do watch it and see what happens. All we can do is wait and see how this epidemic impacts the perception the markets have on ANSYS as a stock, right? It doesn't really matter how it really impacts ANSYS. It's how the market perceives it. So let's see what happens. And speaking of market perception, right before all this happened, ANSYS did release their numbers from Q4 as well as all of 2019, and they held their conference call where they discussed things. So some stats. I highly recommend you go to the ANSYS website, that you go to About ANSYS, and then you go to ANSYS News, and there you can get the press release that has all these numbers. You can take a look at it. In Q4, here's some highlights. They had $486 million in revenue. I remember when that was more than 2 years worth of revenue. It was fantastic to see. They saw a 13% growth in what they call annual contract value. That's the amount of money they make on a given contract. For the whole year of 2019, they did $1.5 billion in revenue. Yes, that's $1.5 billion in revenue. It was fantastic. They did $431.3 billion in profit, which is a 35% profit margin. And that was 12% growth in that annual contract value. They currently had, at the end of 2000, shouldn't say currently had, they had at the end of 2019, $872 million in cash. So this coronavirus thing may slow down some of their business. We'll see. I'm not quite sure how much it's going to impact it, if at all, because this is a tool that's used over the long term. But if it does have there's some panic in the marketplace out there, they can ride out this storm. They've only got $433 million in long-term debt on top of that $872 million in cash. So some quick math on where the money's coming from. If you take a look at that press release and look at they split out software sales versus what they call support and services revenue. Of that $1.5 billion, 46% was software license sales and 53% was support and services. So that recurring revenue of support and services still continues to be a strong part of the company. They also spent $298 million, which is up from $234 million. So, that's a 63, do the math on the fly here, $64 million increase in research and development. Now, this is what we as users love to see, is more money spent on R&D. I'm no expert, but these are strong numbers and show good things to come. The overall market will go up and down, as we all know, but ANSYS looks really strong. So a good place to be if your career like mine does depends on it as a tool, which is fantastic. So ANSYS news. Speaking of all the money they have in their R&D spend, they used some of that R&D spend to buy another company. The company is called Numerical, which is a cool company name. I kind of like that. So it's got, numerical and Luma because it's a photonics company. Clever name. They do chips, diodes, lasers, those sort of things as to the devices that create light, so they can calculate what kind of photons come off of it and what kind of heat is generated and all that stuff. Also, they can model how it's transmitted. So they have full multiphysics. It looks like I'm not an expert in this area. This is definitely the more optic stuff they add, the more out of my comfort zone I get a little bit. But I'm learning as I go as well. So soon I'll have my head around this. But looking at it, it looks like it's a multiphysics tool that does electromagnetics, heat transfer, and other physics that they need to model these devices. It should complement well with our other optical tools as well as our multiphysics simulation capabilities. So we can get loads. Those of us who do thermal or stress or heat transfer or fluid flow, we can get our boundary conditions from this tool or supply them with boundary conditions. It looks pretty comprehensive. It's a nice looking website. Just Google Lumerical. It's Lumerical. Or again, go to the ANSYS news page and you can find the name and the press release there. They already have an interface for some of the ANSYS tools, as well as, which is very important in the optical space, ZMAX. So welcome to the ANSYS family, Numerical people. We've already got some customers that have shown some interest in this tool because they design or use photonics devices. So it's a nice fit, and making that capability even broader and better. Also worth noting is that ANSYS Corporation won an award because of the strong representation of women on their board of directors. And this is nothing new. ANSYS has always had great female representatives on the board of directors, and that's just continued to grow over time. And I've interacted with only a few of them, the ones that work for ANSYS, but it's been a great for the company. Obviously, it's worked. And even cooler news, ANSYS Inc. has a new logo. We really like it. It's much more modern looking. It's got a cleaner font. It's got rid of that black box behind it, which was kind of a pain in the rear for those of us that had to use the logo. So we're really happy about it. The other thing that changed when they changed the logo is it's not an all caps logo. It's capital A and SYS in lowercase. So we no longer have to hold down the shift key or the caps lock key when we type ANSYS in. Yay! So it's capital A now. So that's fantastic. Check out the website if you want to see it. It's right there on the homepage, and you can see it on some of the literature that we're sending out as well. So that happened a couple weeks ago. And PADT in the news, we've got two bits of news to share. We were just, speaking of ANSYS, recertified as an ANSYS Elite Channel Partner. This sets us above many of the other channel partners. There's different levels of channel partners, and PADT is very proud to be an Elite Channel Partner. To get this rating, we don't have to just meet some sales goals. That's part of it. But more importantly for me is that our salespeople have to complete training and pass certification tests, not only on how they sell, but the products that they sell. And on top of that, our engineers who do pre-sales as well as technical support have to pass certification tests across all the products we sell. So until we show them that we know how to sell, support, and really be experts in the tool, we don't become an Elite Channel Partner. So we like this certification program because we're very proud of how well our salespeople and engineers have done over the years that we've been an Elite Partner. So congratulations to all of them for that. We also, not quite ANSYS news, but it might be useful to you folks, is we released something we call the 3D Printing Glossary at 3dprinting-glossary.com. And it is, like the name says, a glossary of 3D printing terms. There's over 250 terms defined. I've got 50 more in the hopper that I got to write definitions for. But take a look at it and use it. If you're writing about 3D printing, if you're puzzled about some of the terms that are used by the experts in the field, it's all defined there, and it's all linked with hyperlinks and all that stuff. It's a nice tool we found on the internet that we paid for to present it in a nice format. Also, if you've got some terms that aren't there, there's a form to send them to us. We'd love to add to it. We'd like to get to 300 soon, and maybe someday 500 different terms. So check that out, 3dprinting-glossary.com. Publication-wise, I picked 3 articles that I liked in the ANSYS blog since the last time we talked. The first one was a really nice article on modeling multi-phase flow and how easy it is to do. Those of us who are not necessarily everyday CFD people, or maybe CFD people that specialize in one area, get a little fearful sometimes of multi-phase because you've got that, phase transition in it. But it's a really good article about how it's actually called, you don't have to be an expert to model multi-phase flow. So they've made it much easier and powerful in the CFD products at ANSYS. So check that out. There's also a look at solving in the cloud called The Truth About ANSYS Simulation in the Cloud and HPC. I liked it because we often get the same questions over and over again when we tell our customers, hey, you can run in the cloud now. You should be running in ANSYS Cloud or in one of these other providers. And we get the same questions over and over again. Well, what about security? What about speed? What about file transfer? And they actually tell the truth about all those. It's a nice, honest article. It's called The Truth About ANSYS Simulation on the Cloud and HPC. Check that one out as well. And then my last one that I liked is called For Expert Ways to Improve Electric Car Ranges with CFD. So if you have customers like we do, or you are a maker of electric cars, it's kind of useful to know. But I found it very important, very useful when I was thinking about other things where I want to increase the efficiency of. So electric cars are just one example of how CFD can increase the efficiency. We often think about, it's electric car, electromagnetics, weight. These are important as well, but CFD plays a role, not just in drag as well. So check that out. It might be useful even if you don't work with electric cars. We published an article. Josh Stout, actually, he was on our podcast recently. He's a new hire here at PADT, and he's been getting his expertise level up on the IcePack tool set, and especially on how IcePack works in the new electronics desktop. Well, electronics desktop is not new, but IcePack in electronics desktop is new. So they're moving it from the old interface into that interface. It's a better home for it. And he shared why it's better, why you should be taking a look at it, why it's time to make that jump. So if you use IcePack, you should be looking at moving. Check this article out. And if maybe you're one of those people that looked at IcePack a couple years ago and went, ooh, this interface, it looks like it's 20 years old, because guess what? It was 20 years old. They've got a new interface now, better geometry interface, and it speaks electronics rather than speaking CFD. So that's another advantage of it as well. So take a look at IcePack again if you haven't in a while. Check out Josh's article. And I actually will say it because it's going out tomorrow morning when many of you will be listening to this podcast. He wrote a great article about doing topological optimization using Discovery Live. It's really cool. We've talked about it before, Discovery Live is this really fast solver. And with the topological optimization, you can get some really good hints on how your shape should progress very, very quickly. It's really cool. Check it out. That'll be publishing tomorrow morning. And that's again by Josh. What are events that are coming up? Well, we've got a webinar. You can do that from your desk. You don't have to worry about travel restrictions. That is on the 25th at 11 Phoenix and Pacific time. It's called MAPDL, Elements, Contacts, and Solver Updates in ANSYS 2020 R1. So we're there now. We're taking a look at what's new and special about contacts and solvers in the new release of ANSYS. It's always an interesting one, as well as new elements. That's always my favorite, but I'm a nerd. If it's not canceled, we will also be at the 2020 MedTech Conference in Arizona. This is put on by the Arizona Technology Council, and it's going to be on the 26th from 1 to 6:30 at venue 8600 up in Scottsdale. It's a great venue. It's a great event. It's one of my favorite of every year. Everybody that does medical devices and medical software actually gets together here in Phoenix, and I'm doing a talk about 3D printing, where I will also talk about simulation for 3D printing, but mostly talking about how we use 3D printing in the medical space. So do check that out if you're here in town. And then also, we're going to be at the 36th Annual Space Symposium at the Broadmoor Hotel in Colorado Springs, Colorado. That is at the end of the month, if it's not canceled. So we are watching that very closely. That is an international conference. It is large. It is a small space. There are major sponsors that, as happened with South by Southwest, that may pull out. So I'm hoping that we can hold it, but we're going to go with caution. Whatever the experts recommend, we'll go with, or if they cancel it, of course, we won't go. So if it does happen, we hope to see you there. If not, we will see you at the rescheduled time. And that is it for this podcast. Again, I apologize for being a day late. Thank you very much for listening. Don't forget to subscribe to PADT's emails at www.padtinc.com/opt-in. Spread the word about the podcast. Let people know, and don't hesitate to reach out. And remember, wash your hands. Wipe down that meeting room keyboard and mouse before you use it. You don't know who was there before you. Keep 6 feet. My favorite CDC advisory is keep 6 feet away from other people. As a simulation engineer and an extroverted introvert, this is wonderful. It should not be hard. And in my opinion, it's a great excuse for me not to have to talk to people face to face and sit in front of my computer where I feel much more comfortable. And of course, if you are sick, please stay home and get better. We need you as a listener. And I mean that, not just joking, but the truth. Take care of yourself, take care of your families, take care of your coworkers. And we will talk to you in 2 weeks. Thank you for joining us for the All Things ANSYS podcast, episode number 58. As a reminder, this podcast is not affiliated in any way with ANSYS Inc., and the opinions expressed are those of the people on the show only and not of their current or former employers, especially when I talk about stocks. I don't know what I'm talking about. For more information, visit www.padtinc.com/blog, and please share your thoughts and questions through an email to podcast@padtinc.com. See you next time.